All right, so get ready, because today we're going deep, really deep, into Einstein's theory of relativity.
Uh-oh.
I know. Relativity.
Sounds a little intimidating.
It does. It can be, to be honest.
Yeah.
But don't worry, we're not going to get lost in the equations.
Yeah.
We have an expert here who's going to guide us through it. Make it actually kind of fun.
I'll do my best.
I have faith in you. So, Einstein's theory of relativity.
Right.
It's not just one theory. It's actually two.
So it is.
Spatial relativity and general relativity. And today, we're going to start with, well, the special one.
Yeah, the special one came first.
It did, back in 1905. And what's amazing is that this whole theory is based on two, like, super simple ideas.
Yeah, just two postulates.
Postulates, I like that fancy word.
Well, they're like the foundation.
Our foundation, yeah.
Of the whole theory.
Okay.
So what's the first one?
Okay, first one. The principle of relativity. It says the laws of physics are the same for all observers, moving at a constant speed. So, like, no matter how fast you're going, as long as it's steady.
Yeah, no acceleration.
No acceleration. Physics works the same way.
Exactly.
Okay. So, like, if I'm on a, I don't know, like a bullet train or something, and it's moving really fast, but it's smooth, no jerking around.
Smooth ride.
The laws of physics inside that train are going to be the same.
Same as outside.
As if I was just standing still.
Exactly.
Okay, that kind of makes sense. It's all relative, right?
It is. That's the name of the game.
Okay, but the second one,
All right.
this is where things get a little
This is where it gets weird.
weird, trippy, mind-bending.
Mind-bending, yeah.
Okay, lay it on me. What's the second postulate?
The second postulate says that the speed of light in a vacuum is constant for all observers.
Okay, so the speed of light,
Doesn't change.
it's always the same,
Always the same.
no matter what.
No matter what.
Okay, so even if, let's say I'm, I don't know, flying in a spaceship
Okay.
at like half the speed of light,
Super fast.
super, super fast, and I'm going towards a beam of light, that light is still going to be moving away from me.
Yep.
At the full speed of light.
That's right.
What? That doesn't make any sense. Like, if I'm driving towards another car, it looks like it's coming at me faster.
Right.
But with light, it doesn't work that way.
Nope. That was a really, really radical idea.
It's like the universe has a speed limit.
It does, and that speed limit is the speed of light.
Nothing can go faster.
Nope, nothing.
So what are some of the, like, crazy consequences of this?
Oh, there are many crazy consequences.
Give me one, a good one.
Okay. Let's talk about the relativity of simultaneity.
Relativity of simultaneity. Okay.
Big word, but it's a cool concept.
Break it down for me.
So basically it means that two events that seem to happen at the same time
Okay.
for one person might not be simultaneous for another person who's moving relative to the first person.
Hold on. So you're saying, like, two things happen at the same time for me,
Yeah.
but not for someone else who's moving.
Yeah, if they're moving relative to you.
Wait, so you're telling me simultaneity, like something that we just take for granted?
Yeah, it seems so basic.
That it's like, no, that's not actually a thing.
Not an absolute thing.
It's relative.
It's relative, yeah.
Okay, I need an example. I need to wrap my head around this.
All right. Imagine you're standing still.
Okay, I'm standing still.
And you see two lightning bolts strike the ground.
Okay, boom, boom.
One on your left, one on your right,
All right.
at the exact same time.
Okay, same time for me.
But now imagine someone's on a train speeding past you,
Okay, there's a train going by.
moving towards the lightning bolt on the right.
Okay, towards the right one.
They're going to see that lightning bolt hit the ground first
Why?
because they're moving towards it,
So they're closer to it.
closer to it. And light takes time to travel.
Oh, so the light from the right lightning bolt reaches them sooner.
Exactly.
But for me, standing still in the middle, it looks like they happen at the same time.
Exactly. So for you, it's simultaneous.
But for the person on the train,
It's not.
it's not. Their reality is different.
Different perception of time.
This is too much, and this is messing with me.
Yeah, it's mind-blowing.
Okay, so what other crazy stuff happens because the speed of light is constant?
Oh, we're just getting started.
All right, hit me with another one.
Another mind-blowing consequence. Time dilation.
Time dilation.
Basically, time slows down for things that are moving really, really fast.
Wait, so like time itself is slowing down?
Relative to a stationary observer, yes.
I think I'm going to need another example.
All right, let's go back to our spaceship.
Okay, I'm in my spaceship.
We're blasting off into space.
Going super fast.
Nearly the speed of light.
Okay, almost breaking the speed limit, but not quite.
Exactly.
So what happens to time?
From the perspective of someone back here on Earth, time is passing slower for you.
Slower for me.
Right.
So, like, if I spend, let's say, a year in space,
Yeah.
flying around at this crazy speed.
When you come back to Earth.
More than a year will have passed here.
That's right. It's like you've traveled into the future.
It's like a time machine.
In a way, yeah.
That is so wild.
And there's one more consequence I have to mention.
Okay, I'm ready.
Length contraction.
Length contraction, what's that?
Objects moving at high speeds, they actually appear shorter.
Shorter, like squished.
Yeah, in the direction of their motion.
So if someone's watching me zoom by in my spaceship.
They might see your spaceship looking a little compressed.
Compressed.
Yeah.
But I wouldn't feel any different inside. Right?
Yeah, it's not like you're actually shrinking.
It's just how they see me.
It's all about perspective, how space and time are relative.
Relative, not absolute.
Exactly.
Okay, my mind is officially blown.
I told you it would be mind-bending.
This is like next level stuff.
It is, but we're just scratching the surface.
Wait, there's more. I thought we covered relativity.
We've covered special relativity.
Oh, right. There's also general relativity.
That's where we bring in gravity.
Gravity. Okay, things are about to get even weirder, aren't they?
Oh yeah, general relativity is where Einstein really took things to the next level.
All right, I'm ready for it. Bring on the gravity.
So general relativity, it basically expands special relativity to include gravity.
Okay.
And the big idea here, the really groundbreaking thing that Einstein realized is that gravity is not actually a force.
Wait, what? Gravity's not a force?
Not in the traditional sense.
What does that even mean? I mean, I feel gravity pulling me down right now.
You do, but Einstein saw it differently.
Okay, how did he see it?
He saw gravity as a curvature of space-time.
A what of what now?
Curvature of space-time. It's like, imagine a bowling ball on a trampoline.
Okay, I can picture that.
The bowling ball creates a dip in the trampoline, right?
Yeah.
Now, imagine that trampoline is space-time.
Okay, space-time trampoline.
And the bowling ball is a massive object.
Like the sun.
Exactly like the sun. The sun's mass is warping space-time around it.
Just like the bowling ball makes a dip in the trampoline.
Precisely.
So you're saying gravity isn't a force pulling things down?
It's not a force in the traditional sense.
Yeah, but objects are just following the curves of space-time.
Yeah, like they're rolling along the dips and curves of that cosmic trampoline.
So it's like Earth isn't being pulled towards the sun.
Not in the way we usually think of it.
It's just following the curve that the sun has made in space-time?
That's a great way to visualize it.
Okay, that's pretty wild.
It is, and it gets even wilder.
Oh no, how can it get wilder than this?
This warping of space-time, it doesn't just affect objects.
What else does it affect?
It affects light.
Light. Wait a minute. Light travels in a straight line.
Light travels in a straight line through space.
Yeah.
But space itself is curved.
Oh, right. Space-time.
Near massive objects.
So the path of light gets bent.
Exactly. It's like a cosmic game of billiards.
With a warped table?
Exactly.
So light gets pulled in by gravity?
Not quite pull.
But it's bending and changing direction.
It's following the curvature of space-time.
Okay. But how do we know this is actually true? It sounds like, I don't know, science fiction.
It does sound like science fiction, but we have proof.
Proof. Like real evidence.
Yeah. One of the first big confirmations of general relativity came from observing starlight during a solar eclipse.
A solar eclipse? What does that have to do with anything?
Well, during a solar eclipse, the moon blocks out the sun's light, right?
Yeah.
So you can see the stars that are behind the sun.
Oh, okay.
And because of the sun's gravity bending the starlight passing by it,
The starlight bends.
those stars appear slightly shifted from their usual positions.
So we're seeing them in the wrong place.
Not the wrong place, but a slightly different place than they would be if the sun's gravity wasn't bending the light.
And that shift, it matched what Einstein predicted with general relativity.
Exactly. It was a huge victory for Einstein and his theory.
That must have been amazing to see his predictions come true.
Yeah, it was a big deal.
So wait, if gravity can bend light,
Mm-hmm.
does that mean there are places where gravity is so strong
Yes.
that light can't even escape?
Yes. That's exactly what a black hole is.
A black hole. Okay, that's a topic for another deep dive, I think.
Definitely.
But this is all incredible stuff. Einstein was a genius.
He was a true visionary.
He completely changed how we understand the universe.
Absolutely. He revolutionized our understanding of space, time, gravity,
And everything.
the whole shebang.
Well, listeners, I think we've covered a lot of ground here today.
We have
We've explored some pretty mind-blowing concepts.
some of the most mind-blowing concepts in all of science.
And we even talk about how these crazy ideas are actually backed up by real-world evidence.
Yeah, relativity is not just some theoretical idea.
It's a real thing.
It affects our universe in profound ways.
And the craziest part is, we're not even done yet.
There's more.
Oh yeah, there's more. Because what's really amazing is that relativity, it's not just some abstract idea that physicists think about.
It has real-world applications.
Real-world applications,
Well,
like what?
Things that affect your everyday life.
Okay, now I'm really intrigued. You're saying relativity is affecting my life right now.
It is, and we're going to dive into that in the next part of our deep dive.
So, if you want to find out how relativity is secretly shaping your world,
You're going to have to stick around.
stay tuned for more relativity adventures.
The journey continues. Welcome back, everybody. I hope you're ready for more relativity.
Oh, I'm ready. My mind is already kind of blown from the first part.
Good, good. Because we're about to see how this crazy theory actually affects your everyday life.
Okay, now I'm skeptical.
Yeah.
How does something like, bending space-time affect my daily routine?
All right, let's talk about something you probably use every day.
Okay, hit me.
GPS.
GPS. You mean that thing on my phone that tells me how to get to the grocery store?
That's the one.
What does that have to do with relativity?
More than you think.
Okay, enlighten me.
So GPS relies on satellites.
Right, orbiting the Earth.
Exactly, way up there in space.
And they send signals down to my phone.
Yep, to pinpoint your location.
I get that part.
Yeah.
But where does relativity come in?
Well, remember time dilation?
Oh yeah, time's slowing down for things moving really fast.
Those satellites, they're moving pretty fast.
Relative to us here on Earth.
Exactly.
So time is actually moving slower for those satellites.
A tiny bit slower, yes.
But slower nonetheless.
And that tiny difference, it matters.
For GPS.
Big time.
Really? Why?
Because GPS relies on super precise timekeeping to calculate your position accurately.
So if the satellite's clock is running a little slow,
it would throw off the whole calculation.
How much are we talking here?
Without accounting for relativity, GPS would be off by kilometers.
Kilometers. So it wouldn't be just a little inaccurate, it would be completely useless.
Pretty much.
So my little GPS device, it's basically a relativity machine.
In a way, yeah. It's got to account for those relativistic effects to work properly.
That's wild.
It is, and it shows how these mind-bending theories
that seems so abstract.
Actually have very practical applications.
So relativity isn't just for physicists anymore.
Nope, it's part of our everyday lives.
Okay, that is mind-blowing. What other examples are there?
All right, let's talk about something a little less everyday.
Okay.
Particle accelerators.
Particle accelerators. Those giant machines that smash atoms together.
Those are the ones.
What does that have to do with relativity?
Well, particle accelerators, they're essential for physics research.
Okay.
They're how we study the fundamental building blocks of the universe.
So like protons, neutrons, electrons, all that stuff.
Exactly. And to do that, they accelerate particles to incredibly high speeds.
Like close to the speed of light.
Oh, yeah, we're talking serious speed here.
So we're back in the realm of special relativity.
We are. Length contraction, time dilation, all those effects come into play.
So those particles, they're actually experiencing time differently.
They are. And their mass is increasing, and their length is contracting.
Whoa. It's like they're living in a different reality.
Kind of, yeah. And scientists have to take all of that into account.
To control those particles.
And to interpret the results of their experiments.
So relativity is playing a crucial role in cutting-edge science.
It is. It's not just some theoretical curiosity, it's a vital tool.
Okay, I'm officially convinced. Relativity is way more important than I ever realized.
It's pretty amazing stuff.
But I have to ask, what if scientists hadn't figured this out? Would our world be that different?
Honestly, yeah, it would be a very different place.
Really? How so?
Well, for starters, we wouldn't have GPS.
Okay, that would be a bummer.
Right. And a lot of our modern technology wouldn't work properly.
Like what kind of technology?
Anything that relies on precise timing or high-speed calculations.
So computers, smartphones, all that stuff.
Potentially, yeah. And our understanding of the universe, it would be fundamentally flawed.
So we owe a lot to Einstein and his crazy ideas.
We do. He showed us that the universe is far stranger and more wonderful.
And more complicated.
Than we could have ever imagined.
Well, listeners, we've explored how relativity is woven into our everyday lives.
From GPS to particle accelerators.
And next, we're going to dive even deeper.
Even deeper.
Into some of the big questions raised by relativity.
The really big ones. The ones that make you question the nature of reality itself.
So buckle up. It's going to be a wild ride. Welcome back, listeners, for the final part of our relativity deep dive.
We've covered a lot of ground.
We have special relativity, general relativity, GPS satellites, even particle accelerators.
We've seen how relativity isn't just some abstract theory.
It's woven into the fabric of our lives.
And the universe.
But now it's time to get philosophical.
Oh, I like where this is going.
Me too. Because relativity, it doesn't just change how we see the universe, it changes how we see ourselves.
It really does.
It makes you question everything.
Like what?
Like, if space and time are relative,
As Einstein showed us.
what does that even mean for, like, our perception of reality?
It's a deep question.
Is everything we experience, is it all just, like, an illusion?
Well, it's not an illusion in the sense that it's not real,
Okay.
but it's definitely relative.
Okay, so how do I wrap my head around that?
Think about it this way. We're used to thinking of time as this absolute thing.
Like a universal clock.
Exactly. But relativity tells us that our experience of time, it's deeply connected to our motion
How fast we're moving.
and the gravitational fields we're in.
So time is not a constant.
It's not this fixed, unchanging thing.
It's more like
It's flexible.
flexible,
Yeah, it can speed up or slow down.
depending on where you are and how fast you're going.
Exactly. Remember those astronauts we talked about?
The ones in the spaceship.
Zipping around at almost the speed of light.
Yeah, time was moving slower for them.
Relative to us here on Earth.
So for them, time is literally passing at a different rate.
It is, which means their perception of the universe is different from ours.
Whoa. Okay. So whose perception of time is right?
That's the thing. There's no right time.
There's no universal clock.
Nope. Relativity suggests that there might not be a single now.
That everyone experiences at the same time.
Exactly.
So like, my now is different from your now.
In a way, yes.
This is too much for my brain.
It's a lot to take in.
It is. It's like mind-blowing.
But it's also incredibly exciting.
Exciting. How is this exciting?
Because it means the universe is far more complex and interconnected than we ever thought.
Okay, I can see that.
And it means that our experience of reality is just one perspective among many.
So there are other realities out there.
Not necessarily other realities, but other ways of experiencing this reality.
Based on your motion and gravity.
Exactly.
Wow. Okay, I need a minute to process all of this.
Take your time.
This is heavy stuff.
It is, but it's also incredibly beautiful.
Beautiful.
Yeah, it shows us just how vast and mysterious the universe really is.
And how much we still don't know.
Absolutely.
Well, listeners, we've come to the end of our relativity deep dive.
It's been a wild ride.
It has. We started with a simple question.
What is relativity?
And we ended up exploring the very nature of space, time, and reality itself.
Einstein's theories, they opened up a whole new way of seeing the universe.
And they continue to challenge us, to push the boundaries of human understanding.
They remind us that there's always more to learn, more to discover.
So the next time you look up at the stars,
Or use your GPS.
remember the incredible legacy of Einstein's relativity.
And keep asking those big questions.
The questions that make you wonder about the universe and your place in it.
Keep exploring, keep learning,
And never stop being curious.
because the universe is full of wonders.
Just waiting to be discovered.
Thanks for joining us on this journey.
Until next time, keep looking up.